Hi class, Mr. Hofstad here with our 7th lesson of Unit 5, talking more about gravity and especially Newton's law of gravitation, or Newton's universal law of gravitation. We call it universal because it applies to any two masses. We usually just think about gravity in terms of planets, right? And we feel the gravity of Earth, right, more than if we were on the moon. There'd be less gravity there. This all has to do with gravitational force between any two objects. So it's a really large object. It's going to have a much larger gravitational force, which is why we're so used to thinking about it only on kind of a larger scale, like a planet. But Newton actually discovered that this force of gravity, Fg, which we're very familiar with at this point, should exist between any two masses, right? Even if we have two pencils sitting beside each other. He theorized that those should be exerting gravitational force on each other. Obviously, it's just so much less force than the force between the ginormous Earth and them that nothing will come to be. So these two forces in any gravitational force setup are equal and opposite. So when we're standing on Earth, we obviously feel the force of the Earth on us. We're also applying a force back on the Earth. It's just so small compared to the mass of the Earth that nothing will really change. So where does this force come from? What does it look like? You can almost think about it. Don't get too confused here, but it's almost like a magnetic force between two magnets that are held close together. But instead of being magnetically charged, all they need to have for gravitational force is mass. So any object with mass, here I'll get a bit out of the Physics 20 mindset, think forward a bit to Einstein, and he theorized that gravity is actually the result of ripples in the time-space continuum, and anything with mass will create a little divot in the time-space continuum, and those divots in the continuum kind of attract each other to other divots or dents in the time-space continuum. You can check out some videos on this, right? If you stretch out a piece of lycra or some spandex stretchy fabric and place marbles in them, if you think of the fabric as the time-space continuum, the marbles are the objects with mass. They're going to sink in a bit, right? And they're going to gravitate towards the other objects. And that moving and that force between the two objects with mass is our gravitational force. So that's all the conceptual stuff. Now let's get into the mathematical stuff. This formula is given on your formula sheet. This constant G is Newton's gravitational constant, and it is even given to you on the back of your formula sheet under constants. 6.67 times 10 to the negative 11, with all of the units that will end up canceling out, right, and resulting with us having newtons. What I mean is the meter and meter will cancel out with the meter squared. Sorry, mass and mass kilogram cancel out with kilogram squared. Radius squared cancels out with meter squared. We're left with newtons. I'll show an example of that below, but let's quickly dissect this. So our gravitational force, now we're not just looking at the force of gravity on Earth. This is between any two masses, M1 and M2. So I guess one of those masses could be the Earth and the other mass could be us. And if we calculated it, we could find the force of gravity, right, which would be the same as doing mass times gravitational acceleration. But here we can also work with two objects that are on Earth, right, or two objects out in space, or between the moon and the Earth, anything really. As long as it has masses, two masses, we can calculate the gravitational force using the distance squared, right, both masses multiplied, and this gravitational constant. So M1 and M2 need to be in kilograms. They're the mass of both objects. R is the distance, and whenever we work with distance, we want meters. And gravitational constant is given in our data sheet under the constants. So let's do an example. We have our two objects sitting side by side, M1 and M2. They have equal masses, so M1 equals M2 mass-wise. We're looking at them being a distance r of 17 centimeters apart, or 0.17 meters, because we need our standard unit for distance. They tell us the force of attraction, or the force of gravitational attraction between them, is 49.2 micronewtons. So that little mu, that weird looking u, means micro. So if we look on our formula sheet, on the back we have our prefix. We could find the symbol micro, and it says it's times 10 to the negative 6. So we have 49.2 times 10 to the negative 6 newtons. All right, now we're just needing our standard equation for gravity. Force of gravity is Newton's gravitational constant, mass 1 times mass 2, all divided by their distance apart squared. So what are we looking for? We want to determine each mass, right? So since M1 and M2 are equal, right, we could really rewrite this as mass times mass, or mass squared over radius squared, because M1 is equal to M2. They're the same. I'm just going to use it as a generic M for mass. And I'm going to try to solve for a mass. So I'll need to multiply by radius squared. So I have my force of gravity times radius squared divided by gravitational constant. We have a square root there. So I'm going to square it, and I'm left with the square root of 49.2 times 10 to the negative 6 times 0.17 squared. So this would be in newtons, this would be in meters, becoming meters squared, and our gravitational constant 6.67 times 10 to the negative 11, and that would be Newton meter squared per kilogram squared. So that's all being square rooted. Let's take a look at our units. Our newtons will cancel out, our meters squared will cancel out, and our kilograms will be kicked to the top, and they're being square rooted. So our final answer will be in kilograms. Good, that's what we're looking for with mass. And it comes out as 146 kilograms. So these pretty big masses, right? This is as heavy as at least 2 people, is only exerting 49.2 micronewtons of force. So very minuscule force. You need extremely large masses, like for instance the mass of the Earth, which is 5.98 times 10 to the 24 kilograms, in order to apply any significant force. So each mass, M1 equals M2 equals 146 kilograms. Both masses are weighing in at an equal 146 kilograms. Okay, back to our notes. And back to another example. We have to determine the net gravitational force on M2. So it'll be really important that we draw this one out carefully. So we have M1 is going to be exerting a force on M2, but at the same time M3 will be exerting a force on M2. So each gravitational force is going to be equal and opposite. So M1 will be attracting M2. We'll call that force of gravity of 1 on 2. And this would be the opposite one, force of gravity of 2 on 1. We're more worried about this one here. And on the other side, we have the force of gravity of 3 on 2. and the opposite and equal force of gravity 2 on 3. Okay, so those are our two important ones. Those are the ones that are acting on our system of mass 2, which is what we're trying to find the net gravitational force on. So we're given all of the masses. Mass 1, this guy is 4,000 kilograms. Mass 2 is 6,000 kilograms. And mass 3 is 5,000 kilograms. And we have a distance of, so we'll call that R12, R23, where the radius between 1 and 2 is 15 millimeters or 0.015 meters, right? Times by 3 we get millimeters, 1, 2, 3. And our radius between 2 and 3, or the distance between 2 and 3, we think about it as radius because these are fields. We'll get into that next lesson, but you'll often hear me interchangeably call them distance and radius because it essentially means the same thing here. And this one is 10, so 0.01 meters. So the net gravitational force on M2 will be, if we say our reference system, right is positive, left is negative, F net on 2 is going to be Fg32 minus Fg21. Alright, so we need to calculate Fg12. So the force of gravity between masses 1 and 2, which will be a gravitational constant m1, m2 over distance squared. So we'll just throw in all of our numbers. We got 6.67 times 10 to the negative 11. We have our first mass, which is 4,000, our second mass, which is 6,000, and we're dividing it by 0.015, our distance, squared. So that'll be meters. That'll be our Newton meter squared per kilogram squared. These are both in kilograms, so our final answer will be in newtons, as it is a force, and it's going to be 7.115 newtons left, to the left. Now, between 3 and 2, we're going to use the same formula, but different masses, mass 2, mass 3, and our different radius. So that was distance between 1 and 2. This is distance between 2 and 3. Same coefficient of gravity, negative 11. Two new masses, we have 6,000 for mass 2, 5,000 for mass 1, and we're dividing it by our distance, which is now 0.01 meters squared. And this one will be 20.01 newtons to the right. So we can find our net force now. F net acting on 2 is equal to F force of gravity of 3 on 2. That's acting to the right. And we're going to subtract the one that's going to the left, our 1 on 2. So we have 20.01 newtons minus 7.115 newtons, giving us a net force of 13 newtons to the right, as it is a positive answer and our reference system was right is positive. All right. That is all we got. Let us take a look now at our torsion balance. So these are some verifications of Newton's theory of universal gravitation, right? Nothing can be accepted as absolute truth in science. Same goes for gravity. It had to be experimented and verified before people would take what Newton said to be true, and even then there's room for improvement. So Cavendish verified Newton's law of gravitation using this torsion balance. So this came quite a number of years after Newton. Essentially what's happening here is we have this stick with two spheres or two masses on the end hanging by a rope, and as a second mass is brought near it, he's going to measure the rotational speed, right? And through that, and some fancy math that we're not going to get into, determine the force of that motion. So we have our unknowns, or our variables, being the mass of each object and the distance between them. So Cavendish verified this first relationship between our gravitational force and our mass using this first experiment. So in this one, he has the gravitational force directly proportional to the mass. So his manipulated variables here are going to be mass 1, right? You're only going to want to change one thing at a time. So manipulated variable is 1 mass. The responding variable is going to be the force of gravity, Fg, and our controlled variables is going to be the distance between them and the second mass. So we have two controlled variables there. If we're changing both masses, right, it's harder to draw solid conclusions. So when you change one mass, you can see that the force of gravity will increase in a directly proportional way. So the graph would be a directly proportional graph, just a straight line up and to the right. The more we increase mass, the more our responding variable, force of gravity, will also increase. So our proportionality, or our relationship, I will just write out a quick sentence for it. Our Fg is directly proportional to mass. And we can write that as a proportionality statement. Force of gravity is proportional directly. There's our weird fish symbol for proportionality. Fg is proportional to mass. So if mass is multiplied by 3, then Fg is multiplied by 5. Sorry, Fg times 5. So whatever happens to mass, the exact same thing happens to gravity. So when this goes up, so does this. When this goes down, so does this. Okay, that's our relationship between gravitational force and mass. He also looked at the relationship between distance, and we alluded to this a bit last lesson with our inverse squared law. A little bit of a spoiler there. So our manipulated variable is, in this case, going to be distance, and our responding variable is going to be our Fg, force of gravity. And controlled is going to be both masses. We want to use the same masses for each of these, so those aren't changing the force of gravity. In a good experiment, you're only going to have one manipulated variable and one responding variable. So the relationship, proportionality speaking, first I'll do a word statement. Fg is inverse squared relationship, where force of gravity has an inverse squared relationship with distance. And it's not going to let me move it. There we go. Force of gravity is an inverse squared relationship with distance. If we write that as a proportionality, it will be 1 over r distance squared, inverse squared. So if our radius is multiplied by 5, then the gravitational force, so this means we're increasing the distance between the objects 5 times, then the force of gravity will be multiplied by 1 over 5 squared, or 1 over 25. So a huge drop in our gravitational force. And any inverse squared graph will look like this. So as radius gets bigger, gravitational force has a drastic drop, and we approach this asymptote of 0. We'll never actually have 0 gravitational force until we get to infinity, which we can never get to. Okay, our last example is just a proportionality style example. So we're going to have a gravitational force between two masses starting at F. We know that both masses are tripled, so mass is times 3, and the distance is doubled. So our force of gravity, we're going to be using the gravity equation that we've been working with today. And each mass is going to be tripled. So since force of gravity is proportional with mass, if our mass is times 3, then the force of gravity will also be increased 3 times. But we're also doing it for m2 is times 3. So we need to increase force of gravity by 3 again. So we're multiplying by 3 twice. And looking at our distance being doubled, so here we're increasing both mass tripled, or increasing it 3 times. And our distance is inverse squared. So if our distance is doubled times 2, force of gravity is times 1 over 2 squared, or 1 over 4. So our new F, new force of gravity, is equal to our original times 3 from the first mass's increase, times 3 from the second, times 1 over 4 from the radius. So if we started out just with unknown F, we're ending up with 9/4 or 9/4 of that starting F. So our new force of gravity after our masses have been tripled and our distance doubled is 9/4 of our starting force. And that's all we got. Have a good time with this lesson and your homework, and please don't hesitate to ask me any questions.